Hello, welcome to The Naked Scientists with me, Chris Smith, and this week with Dominic Ford. Hello, Dominic.
Hello, and this week we're turning our eyes to the sun, finding out about the hazards the sun's radiation can pose to spacecraft and to electronic technology and power distribution networks on the ground. Plus, in the news, the gene therapy which is improving the sight of those born with an inherited form of blindness, and why conservationists are supporting a licence to hunt one of Africa's most endangered species.
And every week we also post to you a scientific teaser. And this time, since we're going to be talking about the sun, can you tell us how old the light is that reaches us here on Earth from the sun? If you'd like to get in touch with us, you can tweet at Naked Scientists, or you can send us a good old-fashioned email. It's chris@thenakedscientists.com.
The Naked Scientists podcast is powered by ukfast.co.uk.
So a story that I spotted this week, it's in the journal PNAS, and these researchers have shown that people intentionally anger others in order to gain a competitive advantage in certain situations. Now, you might cast your mind back to about the year 2006. It was the World Cup, and it's the final, France v Italy. And Zidane, who is a celebrated French footballer, he's on his final ever match of his career. He's going to take France to victory. He gets insulted by one of the Italian team, and he gets insulted in such a way that he gets very angry. And the result of this anger is a headbutt directed at the Italian player and the sending off of Zidane. And it cost France the match, potentially, because it went to penalties. He's their best kicker, and he got kicked off the field. Now, the question is, did that Italian player wind up the French Supremo on purpose? The evidence now suggests that maybe he did, and this celebrated case is cited by Uri Nisi and also Alex Emas, who are the two researchers on this paper this week, because what they did is they got a whole bunch of students to come into the lab, and they got them to do two tasks, or one of two tasks each. Now, in the first task, it was a strength task. So what they said is, grip this lever, squeeze it as hard as you can, and the person who squeezes it the hardest, they're the winner. So they do the study, and you get a result for the students. Then they randomly choose one of the two students and say, right, now you're going to be able to go home after this is over, but the other guy sitting here, he's going to have to stay behind to do all the paperwork related to the study for as long as you decide he's going to stay here, up to a maximum of 20 minutes, and we'll even give you a financial incentive to make him stay longer. How long do you want him to stay? Now, Dominic, if that was done to you, how would you feel?
Oh, I feel quite annoyed, really.
If I chose 20 minutes maximum for you, right?
Yes.
Okay, so that's exactly what happened. The people found they were angry. So when they did this task again, of course, anger makes people stronger. It's a well-known fact. And sure enough, the angry people squeeze the lever much harder the second time. Pretty obvious, you'd say. Right, in the second task, though, this was what they called a cognitive test. So what they did this time was they said, now, the two of you are going to have a fantasy duel. You're going to be standing a certain distance from each other, and at each go, and you're going to take it in turns, you can either elect to move one pace closer to each other, or you can shoot each other. And the probability of you missing is going to go down each step you take, but it's not going to go down at a standard rate. It's going to change at a non-standard rate. So the closer you get, the higher the probability of hitting the opponent becomes. So therefore, you've got to think about it and think, what's the optimum distance for the odds to be in my favour? And it turns out you've got to be 15 paces in. Now, this time, when they gave them the opportunity to upset or anger the other player, when they actually did the duelling task, the person who was made angry did much, much worse if they got the maximum sentence of 20 minutes of staying late afterwards, compared with the other person, or when there was no such punishment. And when they looked at whether or not it was therefore advantageous, you would assume, right, if it's advantageous and people are strategically making people angry under the right circumstances, in the stress task where there's a strength test, you'd expect them to make them angry less often, because the stronger they are, then the less chance you've got of winning. But if it's a cognitive thing and they've got to think about things, it's in your favour to make someone angry because they won't be able to concentrate. When they look at the numbers, that's exactly what they see, because in the strength task, only 45% of the subjects meted out the maximum anger-inducing 20-minute punishment on the other person, whereas in the cognitive task, it was 63%. And they actually conclude the paper by saying, this suggests that individuals anticipate the behavioural effects of anger and they use it strategically. They're more willing to anger opponents when it will have a detrimental effect on their performance.
In the news this week, we've obviously got the Australian Open tennis, and that's a sport. We're going right back to John McEnroe. There's been this debate about the way that players behave, the way that they perhaps wind up the match officials and their opponents. So is that potentially making their opponents more likely to make mistakes in their choices of shot?
It'll certainly put them off, won't it? But also you could argue in a game where you've got also physical attributes coming to bear, if you're going to hit that ball harder, if you're angry about it, then I think it's 6 of one, half a dozen of another, because it could be that on the one hand there's a detrimental cognitive effect, but there could also be an enhanced effect because you're angry, you can hit the ball harder.
Well, that's an interesting insight into tennis, perhaps. Now, last weekend, the American hunting group for Dallas Safari Club raised $350,000 by selling a hunting licence to shoot one of only 5,000 black rhinos remaining in the wild. Now, you might think that conservationists and animal rights groups would be up in arms, and unsurprisingly, some of them are. But the International Union for Conservation of Nature are actually supporting the sale, and Mike Knight, who's the chair of their rhino specialist group, joins us now from South Africa, where he's the head of planning and development in the national parks. Now, Mike, what is the threat that black rhinos face?
Obviously, we're facing the threat at the moment from escalating poaching that's been driven by the demand for horn in the Far East. Last year, we lost 1,004 animals, most of which in South Africa. But I think obviously the focus of this discussion will be looking at Namibia, who've lost only 2 animals.
So given that there are only 5,000 of these rhinos remaining in the wild, why are you supporting the sale of a hunting licence to actually kill one of them?
Well, the whole thing around rhinos, and particularly rhinos, these hunting applications are focused primarily on males, which we've actually coined as surplus males, and it's primarily the old geriatric males. These males are often involved in fighting. In many cases, females are killed. And in Namibia, for instance, up to 30% of the animals that are lost in Namibia are a result of fighting. And in many cases, that's females. The last thing you ever want to lose in a population that is of that size is to lose the breeding stock and to lose the females. So what we have to do in a situation like this is to try and make sure we do the best for the males. Putting the males onto other land or alternative land has huge cost implications. It's also taking away the opportunities for breeding populations. So really the best way to turn this around is to actually use these surplus males. And remember, there's only 5 animals given in South Africa and Namibia as part of the hunting quota, and that money goes directly back into conservation. So yes, they are in some ways sacrificial, but to the same extent they have great financial returns towards rhino conservation. In the case of Namibia, that money was ploughed 100% back into conservation.
And how's that surplus males come about? Is that behavioural?
It's behavioural. It's black rhino. Black rhinos are notably aggressive. At the moment, in many of the populations, they are distorted towards males, and populations that have the larger proportion of breeding males don't perform as well as those where the proportion of males are less. So what we try and do in many situations is skew the sex ratio in favour of females to get them breeding as fast as we possibly can. And then the question is, what do you do with these surplus males? And in the case of Namibia, the males that they're actually talking about are ones that are often being kicked out of Etosha National Park. In many cases, they put these animals back into the park, but in 90% of the cases, those animals are either being killed or they killed other animals. So the best thing is actually let's try and get a conservation benefit from this. And that conservation benefit is in the form of rands or in dollars, which goes directly into conservation.
What sort of reaction have you had from the international community to this decision to sell this licence?
I think a lot of it comes around possibly from ignorance, not understanding the context in which we're talking about. As you know, Southern Africa follows a sustainable use approach to the wildlife, and you can see that in the amount of wildlife and the amount of land set for conservation. So in the Southern African context, we've had an outcry in many ways to say, yes, the animal could have been auctioned for $1 million but went for $350,000. What happened to the other $650,000 that should have gone directly into conservation? That is money lost to rhino conservation.
And very quickly, what will you spend that money on?
It goes directly into anti-poaching, into training, into monitoring, and improving the situation for rhino conservation.
Mike Knight, thank you very much. That was Mike Knight from South Africa National Parks and the International Union for the Conservation of Nature. So what do you think? Should this hunting licence have been sold? We'd love to hear your reactions. You can email chris@thenakedscientist.com or you can tweet @nakedscientists.
Crowdfunding programs like Kickstarter have been used to raise money for music projects and Hollywood films, but now it looks like they could even be used to raise funding for long-running scientific projects. The so-called Keeling curve is one of the world's longest unbroken records for how much carbon dioxide there is in the atmosphere. But after funding cuts, it's now asking the public to chip in to keep these measurements going. To find out more about this historic archive and the gas that it measures, here's your quick fire science with Kate Lamble and Dave Ansell.
Carbon dioxide, or CO2, is given off whenever any carbon-containing material is burnt, whether that's a candle or a piece of coal dug up from the ground.
The colourless and odourless gas was first identified by Flemish alchemist Jan Baptista van Helmont in 1648, who described it as a gas given off by burning charcoal.
Plants absorb 420 billion tonnes of CO2 every year. That's in almost perfect balance with the amount of gas produced by living things during their respiration.
However, since the Industrial Revolution, humans have been burning fossil fuels which have been buried for millions of years. This now produces around an extra 33 billion tonnes of carbon dioxide every year.
Although this is a far smaller amount than naturally produced CO2, if it isn't absorbed, it'll build up in the atmosphere.
In 1859, John Tyndall discovered that carbon dioxide insulates the Earth, keeping it warm.
This discovery caused some concern. Alexander Graham Bell wrote as far back as 1917 that the unchecked burning of fossil fuels would have a sort of greenhouse effect. He said the net result is that the greenhouse becomes a sort of hothouse.
But the potential of the effect was not appreciated until the 1960s, when planetary scientists studying Venus realised that the very thick atmosphere of carbon dioxide on that planet had caused the surface temperatures to rise to over 450 Celsius.
CO2 concentrations have been measured continuously at Mauna Loa in Hawaii since 1958.
Over the past 56 years, carbon dioxide levels have risen by nearly a third, from 315 parts per million to reaching over 400 parts per million in May 2013. This is the first time in recorded history.
Scientists estimate that the last time the Earth previously reached these levels was 3 million years ago in the Pliocene era, when average global temperatures and sea levels were higher than they are today.
Sadly, if the money cannot be raised and monitoring of the Keeling curve in Hawaii is halted for even a brief time, it will be very difficult to ensure that future measurements are properly calibrated to match the historical record.
Dave Ansell and Kate Lamble, and you can get hold of all of our Quickfire Science episodes as their own podcasts from our website at thenakedscientist.com/quickfirescience.
Just to remind you, we're talking here on The Naked Scientists about the science of the sun and its impacts on the Earth this week, including the launch of the UK's space weather forecasting system, which will go online shortly. David Willits, the Minister for Universities and Science in Britain, will be on the programme to answer our questions about that. If you would like to get in touch, you can email chris@thenakedscientist.com, you can tweet @nakedscientists, or find us on our Facebook page. Blindness-causing diseases of the eye have for a long time been regarded as irreversible, but now scientists have begun to explore whether gene therapy can slow down or even reverse some of the damage. Robert McLaren, an ophthalmologist, is heading up one of these studies at the University of Oxford, and he's published the first clinical findings on his work this week. Hello, Robert.
Hello.
So what's the disorder that you've been looking at specifically?
Well, Chris, we're looking at a retinal degeneration, which is basically a degeneration of the lining of the back of the eye, the light-sensitive sort of film at the back of the eye. And the particular disease is caused by a missing gene on the X chromosome, so it affects males, and it's called choroideremia, which is an original description given to it well over 100 years ago.
And people who have this, what happens to them? How would they know they've got the condition?
Well, quite often we diagnose it as a new genetic mutation, but sometimes there's a family history, so a mother might be aware that her son's going to get it, and the initial signs will be things like difficulty with night vision. That would occur perhaps in childhood, and then gradually around about the age of 10, 11, 12, the visual field, the peripheral vision becomes constricted, and they develop what we sometimes refer to as tunnel vision. So they can see a little bit in the middle, but all around the outside is all dark. This tunnel vision gets progressively worse, and then sadly, by the time they get to 40s or 50s, they then become completely blind.
And how does the intervention, your gene therapy approach that you're cooking up, work?
Well, the patients have this retinal degeneration because they're missing the choroideremia gene, or the CHM gene for short. This gene is normally present in the light-sensing cells and the lining of the back of the retina, the back of the eye. So the principle of gene therapy is, a relatively new concept in medicine. It's actually to try and correct the disease at the genetic level. And in the case of choroideremia, what we do is we make a virus that carries DNA, because viruses do carry, DNA or RNA. That's the properties of virus. Only rather than carrying the viral gene, the virus contains the choroideremia gene, which we've artificially put into it. But nevertheless, the virus on the outside is the same. It retains its same abilities to bind to and infect the retinal cells. It gets into the cells. The virus then releases its payload, thinking it's its own DNA for replication. But in fact, it is the choroideremia gene that goes into those cells. And although we've taken out most of the viral genome, the little bits at the very end which stabilize the DNA and allow it to sit in the cell dormantly for years and years and years, all that is still there. So as far as we're aware, so far, we are actually looking at, in principle, a treatment which should have a permanent, lasting effect.
And you administer this virus into the retina, do you?
Yes, the patients have to undergo an operation which involves, first of all, removing the jelly at the back of the eye and then injecting under the retina a concentrated solution of virus. And, of course, that's a rather tricky bit to do because it's a very delicate process. And one of the concerns in our study at the beginning, we realized that gene therapy is really best applied before the onset of vision loss, before the cells die. So we had to really get the virus into the retina in patients before they'd lost their central vision. And we did that on 4 patients, and unfortunately the vision did recover. And in fact, what was remarkable was that actually we could then see the further improvements from before they'd had the operation once the virus was working. So, it is a combination really of the biological technology of the virus, but also trying to develop the technique of surgery better.
How do you know that it's the virus improving the outcome for these patients and not just the operation or some aspect of having something injected into the eye? Because I presume you didn't do the experiment where you just injected water or something into the eye without any virus just to see what the injection itself does.
No, and of course that's a very good point. It's very difficult sometimes when doing clinical trials to have a true, what we call sham injection. But the eye is quite useful because, of course, we've got the other eye to look at as well. And also we know a lot about the natural history of the disease. So when we initially noticed the quite significant improvements in vision in these patients, with their permission, particularly the 2 who had the largest change, we contacted their home opticians to get their sort of historical vision records over many, many years before the trial, and also an up-to-date vision, just in case, there might have been something different about our trial system. And that verified our findings in the fact that the vision had improved. And this is a disease in which the vision gets progressively worse, and it's very difficult to understand how it could improve by several lines without something going on. And indeed, the effects we've seen in the first patient who gained more than 3 lines of the standard, what we call Snellen chart, the big chart you see at the opticians. He couldn't even see the top letter before the surgery. He can now quite comfortably read the top 2 lines. And that's been sustained now for 2 years. So, it's a very good question. I often get asked this, and I say, well, if it isn't the virus that's doing this, it must be something else. It's still quite amazing. And if it is a sham injection or something similar after 2 years, then obviously it would be difficult to explain through any other reason than the missing gene is now doing its stuff. And of course, the patients, we do notice improvements in the quality of the vision. Certainly, that's certainly the case.
Robert, thank you for joining us and telling us about the work, and we wish you luck with it. That's Robert McLaren. He is from the University of Oxford, and he published that work this week in the journal The Lancet. Dominic.
Now, this week I spotted a paper about emperor penguins, which are the largest species of penguins in Antarctica. They grow to about 120 centimetres high, they weigh 20 to 40 kilograms, and they can live for up to 20 years. But they've been classified as close to threatened by many international conservation groups, and that's because they are completely reliant on the formation of sea ice around the Antarctic continent in order to breed. Each year, as winter comes into Antarctica, the sea around the coastline of the continent freezes to form flat plains next to the ocean, and that's the ideal place for these penguins to breed because they've got dry land or snow on which they can bring up their young, but they've also got easy access to the ocean so they can go fishing and find the food they need. But with global warming, which has been affecting Antarctica especially badly, the question has been, if the sea doesn't freeze in the winter, what would the penguins do? Would they find somewhere else to breed, or would they just not breed that year? And if this were to happen for several years in a row, would these penguins then face quite a serious threat to their population? Now, the last couple of years, 2011 and 2012, have had quite exceptional weather in Antarctica, exceptionally warm spell, probably freakishly warm weather rather than anything to do with climate change. But it's given Antarctic scientists the first opportunity to really see how these penguins behave when their normal breeding habitat isn't there. And they've looked at satellite images from these 2 winters to see what the penguins were doing about the fact that they didn't have this sea ice to breed on. And what they found, quite remarkably, was they found an ice shelf which was 30 metres high up out of the ocean, and there seemed to be a penguin breeding colony on top of this ice shelf. And that's quite a different environment from where the penguins are normally used to breeding. It's fresh water for a start rather than frozen seawater. But also it's 30 metres up. And emperor penguins, they're quite adept at swimming. They're mostly aquatic birds, but they're not actually very good on land. They tend to be rather clumsy. So scaling a 30-metre cliff, you would have thought would be quite a feat for one of these penguins. And looking at these satellite images, they could actually see these penguins had trodden out this zigzagging track going up this side of this ice shelf. They seem to have put quite a lot of thought into the best way to get up this obstacle. And there they were, having chicks on top of it and apparently thriving. So in terms of the threat to emperor penguins from climate change, this is actually quite reassuring. These animals seem to be resourceful and quite adaptable in terms of finding somewhere to raise their young.
But there's more to it than just raising young, isn't there? There's also, they've got to feed, for example, and if there are knock-on effects in the oceans and on their food source, then this actually may impact them. Or what about predators as well? I mean, if you force them to move, you may force predators to move and they might get eaten.
It's a very good point. I mean, obviously this doesn't mean that there aren't serious concerns about climate change in the region and the change that will have on the ecosystems in Antarctica. I think this is to do with how we prioritise our resources towards conserving certain animals. And these emperor penguins have been classified in the past as being close to being threatened. You want to focus your finite conservation resources towards the pressure points where animals may go extinct. And these emperor penguins don't seem to be under quite such threat as we feared they might have been.
Dominic, thank you very much. If you'd like to catch up with any of the stories we've been discussing, you can find transcripts for them and the references on our website at nakedscientist.com/news. We've heard from quite a few of you who are having a go at our quiz. Don't forget that we're talking this week about the science of the sun, and I asked you, as our scientific teaser, how old is the light that reaches the surface of the Earth? Lots of people are plumping, including Amanda, Liz and Ed on Twitter at Naked Scientists and email chris@nakedscientist.com for 8 minutes or thereabouts. But are they right?
You're listening to The Naked Scientist with Chris Smith and me, Dominic Ford, and time to go on to our main topic for the week now, because just before Christmas, the UK's National Weather Forecasting Service, the Met Office, announced that it would begin monitoring the sun's activity to advise space agencies and power distribution companies about the hazards that its radiation might pose.
In just a moment, we'll be talking to one of the researchers from the Met Office who's working on that project. But with us first is David Willetts. He's the Minister of State for Universities and Science, and also Lucy Green. She's from the Mullard Space Science Laboratory at University College London. She works on the sun. Hello to both of you.
Hi.
Hello, Lucy. Now, David, first of all, why are you doing this and why are you doing it now?
We're doing it because when we look at the kind of strategic threats to the functioning of our national infrastructure, we've got space weather now quite high up on the list as something that is potentially disruptive. So it'd be a great advantage if we were better able to forecast it. And secondly, of course, this is just another great example of British science. We have experts who are very good at monitoring solar activity. We are backing projects like Solar Orbiter aimed at understanding the activities of the sun better. And given that we've got scientists working on this, it's right that we should then harness their researches for better space weather forecasting.
How big is that hazard?
Well, we reckon that, as you know, space weather Solar activity seems to come in cycles of 11 or 12 years. The experts talk about the Carrington event back in 1859, which was the first great measurement of this activity, incidentally from Kew, near where I am in London at the moment. And it does look as if when you have these peaks of solar activity, it can be disruptive in several ways. It can disrupt electricity supplies, it can disrupt the grid, and indeed, two of the most significant power outages in the Western world, in Quebec in 1989 and in Sweden in 2003, were linked to high levels of solar activity. So that's an issue, and it's why it's important for our electricity grid and infrastructure. And then secondly, satellites. And of course, we're increasingly dependent on satellites. Now, when I talk to the satellite operators, they don't say that it necessarily you'd suddenly have all your satellites knocked out. You might want to shut them down for a time, and even shutting down a satellite before you and then having to turn it back on could interrupt services that we are all used to delivered via satellites. So there are reasons why having better information that one of these peaks of solar activity is coming would be of great benefit for us.
Lucy, can you tell us a bit about what causes the sorts of peaks that David's referring to?
So the peaks in solar activity, in terms of the activity that the sun produces, you've got 4 different types. You've got solar wind, which can blow very, very strong, be very gusty, and have a strong impact on the Earth's magnetic field. And then with the knock-on consequences, as David has already been saying about, you have solar flares, which are bursts of intense radiation that come towards the Earth, coronal mass ejections, which are these eruptions of plasma and magnetic field, and also energetic particle events. And all of these 4 kinds of activity vary over roughly an 11-year cycle, which we call the solar activity cycle, and they ebb and flow with that. And at the moment, we are at solar maximum.
But David, the cynic in me is saying we're still here. There are 7 billion people on Earth. The Earth hasn't melted down yet, but there must have been many, many of these such events in the past. Why do we need this now?
Yes, I mean, and it is a well-established pattern, as Lucy is describing. I think what we have to recognise is that, first of all, we've got ever greater and more sophisticated electricity distribution systems. And secondly, we are more dependent on satellites than ever before. And third, and which I should have added to the list, there are some issues about aircraft, air travel near the poles, how much exposure to radiation there is for, particularly for pilots and crew who are regularly flying. So there are several reasons why a modern high-tech world is more vulnerable. And I think that it's, given that we have this understanding of the science, what we're doing is investing now in the capability. Out of the science budget, we've put in about £2 million for the IT infrastructure to really harness the data. And we're putting in another £4.5 million or so to deliver operational services. We'll be working very closely with the Americans. And I think it's both a great way of ensuring better advance notice for our infrastructure. It is also pushing forward the frontiers of science and linking science to actual operational requirements like space weather forecasting. And I think that's what many scientists like to see us doing, using their increased understanding of things like solar activity and putting it to practical use.
Looking at it another way, though, £4.5 million, that's what, 1,000 hip replacements. You could probably do a couple of thousand cataract operations and give people their sight back in old age for that same money. There are already people doing space weather forecasting in America. Couldn't we borrow their space weather forecast and make more old people mobile?
Well, the science budget is modest compared with the health budget. And look, I think that the guaranteed £4.6 billion a year we put into science is absolutely the right thing to be doing. We should be incredibly proud of the quality of our science. And within that, I think that space science and understanding solar activity is an area where Britain has high quality science. And then, in turn, although, of course, yes, the Americans have got some of these data sets, Britain brings something to the party. You know, we're not simply people who should be sitting around endlessly saying, well, we can get it off the Americans. We're very good at writing software. We're very good at solar science. We are genuine partners in this project. And like in so many other areas of science activity, if we're bloody good at it, and if we've got these capabilities, it's right to use them. We don't need to simply be dependent on other people.
Fair enough, but I put it to you, I cannot download Downton Abbey on my computer 6 miles outside of Cambridge, despite the fact that some of those companies that you've cited as making Britain foremost in the world are sited not far from where I live, because my internet connection is so appalling. Should we not be pushing more money into getting our population better connected? Because regardless of space weather, if there's a big coronal mass ejection, I'm not going to notice because my technology is in the dark ages already.
I can sense you have a strong personal grievance there, and I would not dispute it. You're absolutely entitled to be frustrated about that. And actually, in a separate bit of government, we are absolutely trying, particularly to tackle some of these not spots and get people properly onto fast broadband connections. In fact, I think we're on track for getting further to that by 2015 than most other advanced Western countries. But the decision was not, I have to say, the decision that came across my desk was not, should we put more money into improving broadband services within 6 miles of Cambridge or into space weather forecasting? That's not quite how government functions. What we actually had an issue was with what's the best way of using the science budget and the budget that I put into the Met Office. And I think this, given that the space weather is actually now on our top 4 or 5 list of national infrastructure problems and risks, it would be a disaster if in a year or two, imagine that we did have power outages. Even, dare I suggest, imagine we have power outages in Cambridgeshire and we hadn't had the advance notice. Now, this is where I'm not an electricity engineer, but my understanding is if they get some advance notice, what they can do is operate the national grid, bring all the air equipment online, operating it so that they can spread the load, and that reduces the risks of outages across the system. So we're insuring you against that risk, and it's worth doing.
Good to hear. Lucy, why does the sun manage to knock out connections and power grids and things?
Well, the sun really is a much larger object than we may appreciate. So what I mean by that is that it has a very, very extended outer atmosphere that reaches out for billions of kilometres through the solar system. So Voyager 1 spacecraft has recently passed through the edge of the sun's atmosphere at about, I think it was over 15 billion kilometres away. So the Earth is sitting in a very variable atmosphere of our local star, and it's changes in this atmosphere that affect the Earth through changes to the Earth's magnetic field. So I mentioned earlier on the solar wind, that is an expansion of the sun's atmosphere. That's what carries it out to these vast distances. And then within that solar wind there are bubbles of magnetic field that get blasted out called coronal mass ejections and these solar flares, and very high energy particle events as well. But really it is effects to the Earth's magnetic field through solar activity within its atmosphere that eventually propagate down to the Earth's surface and then have effects on, for example, the national grid.
Lucy, thank you very much. You're going to stay with us, but thank you very much to David Willetts, who's the UK Science Minister, for joining us to tell us about your initiative in forecasting space weather. David, thank you.
Thank you very much.
You're listening to The Naked Scientist with Chris Smith and also with Dominic Ford. We're talking about the science of the sun. So far, we've heard why scientists, as well as the government, think that it's important to monitor the weather in space. But what are the researchers working on the project actually hoping to achieve? Mark Gibbs heads up the Met Office's new space forecasting team that are being funded by the intervention that David Willetts outlined.
What we're developing at the Met Office is the UK's space weather prediction capability. Space weather is being recognised by the government as being a key risk to the UK. And we've been working very closely with government and a range of sectors that are likely to be impacted by space weather to understand what type of forecasting services they could use to help try and mitigate the risk. And really, this project is about putting together that forecasting system so we can provide warnings and alerts to both government and those key sectors to try and minimise the impact of space weather on their operations.
What is the strict definition then of space weather?
At the moment, space weather's got a definition which is, I think, subtly changing. It has always been the impact of sudden bursts of energy and releases of matter and how that impacts on the Earth's environment and on the technology we use. But now we're very much talking about sending manned missions to Mars, and people are interested very much in the much wider solar system and the whole of what's called the heliosphere, the area of space affected by the sun under the magnetic field from the sun. So whilst obviously we're clearly interested mostly in the Earth, increasingly mankind is interested in what's going on elsewhere in our solar system.
How are you getting all of the data? Are you talking to lots of other organisations like you all around the Earth who are gathering the right sort of information and then you put it all together?
Absolutely. Forecasting space weather, as with forecasting terrestrial weather, is a global effort. So most of the data we're getting are from big international missions, satellite missions launched by NASA or ESA. We share data around the world with a range of partners, and also working with UK partners. We get data from the British Geological Survey on the magnetometers they have across the UK. Probably our most important relationship at the moment is with the NOAA National Weather Service and their Space Weather Prediction Centre. They're recognised as being the global leaders in this field, and we're working very closely in close partnership with them as we're developing our skills and our capability, with the ultimate aim that we will provide mutual backup to each other. Because a big space weather event could have a massive impact on economies, and unlike terrestrial weather, a space weather event could affect large parts of the globe simultaneously. So it's important that we have international resilience. So if there's a big impact in the US, and that means the NOAA Space Weather Prediction Centre aren't capable of producing forecasts, there are other centres globally like us that can sort of step into their shoes and actually provide support to both the US but also other nations around the world.
What will these space weather forecasts look or sound like? If I were to receive one, what would be in it?
They'll be very different from the sort of weather forecasts we're used to. They're very risk focused, so we talk about probabilities of events happening, but we're looking to do things like predict the arrival time of these CMEs, predict the electron fluence levels in the radiation belts where satellites fly, also looking to predict the probability of these solar flares occurring and the HF radio communication blackouts they produce. So we try to talk more in terms of impacts rather than whether it will rain or not. I can't see the day when we'll be putting space weather forecasts on TV, say, because it is for a very specialised market.
And who is that market? I would think the airline industry must be one organisation that are interested, aren't they? Because they might want to change the course of where they send their aeroplanes and how high.
That's absolutely right. They can have issues with radio communications. Any airlines flying directly over the poles, particularly the American airlines that fly to the Far East and vice versa, fly directly over the poles. During even moderate space weather events, they will avoid the polar regions for safety reasons. Other sectors we're working particularly closely with is the energy sector. I think globally the concern around the power grids is probably the greatest risk. We know from the 1989 event in Quebec where they had a region-wide power outage, and again 2003 in Malmo where they had a city-wide blackout. That's the one thing that really causes concern. Other sectors we'll be working with are people like the satellite industry. They want to understand when their satellites are going to be bombarded by higher radiation levels. The satellites are hardened to operate in that, but it is good practice for them to have extra engineers on board and be monitoring the satellites more closely just to make sure that they're performing well.
You've got, 150 plus years of experience of forecasting the weather. You've got 0 years of forecasting the space weather. This must be an on-the-job learning exercise then.
Very much so, very much so. We've done training courses for some of our forecasters because what we've done is we've taken weather forecasters and trained them additionally in space weather as well. And many of those forecasters, we've got about 12 trained space weather forecasters now. And many of them have been over to the United States and sat in the Space Weather Prediction Centre in the US there alongside dedicated space weather forecasters. With a number of those have got decades of experience in predicting space weather. But you're absolutely right. A lot of it is learning on the job. This is the first solar cycle we're all going through, and when we're at the early stage of the solar cycle, we were seeing stuff which was exciting to us. Now we look back, a year, 18 months later, and think, well, why did we get excited by that? That was just a minor blip. We're seeing bigger events happening now. So it is a learning process, and I think we all need to go through a whole solar cycle, the order of 10, 11 years before we can actually say, yes, I'm starting to get real understanding of space weather now. We need that sort of long period of experience before we really can understand the complete picture.
Mark Gibbs, who's the head of space weather at the Met Office.
You're listening to The Naked Scientists with Chris Smith and me, Dominic Ford. And as Mark was explaining, the Met Office is working to compile the best possible observations of what the Sun is doing in order to make predictions of when the Earth may face a particularly strong battering from the solar wind. But elsewhere, scientists are working to understand why the Sun's activity varies in the way it does, in order to form even better long-term predictions of how the Sun is going to behave in years to come. And one of those researchers is Lucy Green from University College London. Now, Lucy, on the surface, the Sun seems a very simple object. It's a ball of gas. It doesn't have solids and liquids on its surface. Why is it so difficult to understand?
Well, it is a very complex object, and I think that's something that's really become apparent to us over the recent decades. So, in particular, with the advent of the space era, which enabled us to put telescopes into space above the Earth's atmosphere and really showed the sun in all its glory. So, prior to the space age, we were viewing the sun just using, mostly using visible light, so the wavelength that our eyes detect. And if you filter or project an image of the sun, you see sunspots. But when we went into space and we started to see the short wavelength, the high energy radiation coming from the sun, which we detected for the first time, the sun revealed itself to be this very complex object which is seething with hot gases or hot plasma, electrically charged gas, but also magnetic fields. And I think that really showed a level of complexity that we've been having to try and understand ever since.
You've hinted there about the unique challenges of observing the sun. Astronomers spend a lot of their time looking at incredibly faint things in the night sky at incredible distances. The sun isn't like other objects for astronomers to study, is it?
No, we are not short of photons. We're not short of light to study. That's absolutely correct. But in a sense, okay, we're lucky with the amount of light we receive from the sun, and we're lucky that we can spatially resolve our local star. We can see the details on its surface and in its atmosphere. But that, again, it adds into this level of complexity that makes the sun such a challenging object to understand. We see it varying second by second, and we see it varying on very, very small size scales. Each time we build a bigger telescope that can see more detail on the sun, we have more questions to answer, and that makes it very challenging.
And you mentioned there sunspots. How are those connected to these explosions of plasma that might get sent out towards the Earth and cause problems for satellites?
Sunspots are really fascinating features. So first of all, we saw them as these dark spots on the surface of the sun, and for several hundred years they were drawn, they were counted, and they were followed on the sun. But then in 1908, an American astronomer, George Ellery Hale, built an instrument that detected the true nature of sunspots, and he realised that they are strong sources of magnetic field, very, very concentrated, strong magnetic fields on the surface of the sun. But these magnetic fields emanate up into the atmosphere. And really, that discovery was the birth of solar physics, because then we became able to understand how the sun is energized, really, because these magnetic fields, and this is sort of an alien concept, I think, really, these magnetic fields that emanate out from the sunspots are able to store energy. And when that energy gets released, it gets transformed from magnetic energy into light or particle accelerations and heating of the gases. When that happens, you get the forms of solar activity that we've mentioned already. So solar flares happen when magnetic energy gets transformed into visible light, ultraviolet light, X-rays and so on. And coronal mass ejections happen when this magnetic energy gets transformed into the kinetic energy of the motion of plasma out into the solar system.
Lucy Green, thank you very much. I want to move now to Joanna Haigh from Imperial College London, because we've had a lot of people getting in touch asking whether the sun's activity can affect the Earth's climate and whether it might affect the climate change that we've all been hearing about in the last few decades. Now, Joanna studies the connection between solar activity and the Earth's climate. And Joanna, we've been hearing a lot about the sun's activity in the form of spewing out plasma into the solar system. When we're talking about the sun affecting climate, is that the activity that we're talking about?
No, it's not. So those solar storms affect a very, very high atmosphere of the Earth. But when we're talking about climate, we're more interested in the sun's electromagnetic radiation, so just the visible and perhaps a bit of the UV light and near-infrared light that gets near the Earth's surface and is warming the planet.
So it changes in the amount of light the sun is putting out?
That's right. So we've heard about the 11-year cycle on the programme already, and there is the amount of energy that comes out of the sun varies by about 0.1% over the 11-year cycle. So that influences the amount of energy received into the climate system.
So with growing evidence for climate change in recent decades, do you think changes in the sun's behaviour could be contributing to that?
It's probably contributing a little bit. but we know enough about the energy coming out of the sun and about the factors that are causing climate change to be able to say that the sun can't be causing recent global warming. It might contribute a small fraction, but it can't be responsible for the whole thing.
So in terms of your work looking at connections between solar activity, the light the sun is putting out, and the Earth's climate, does that mean you're having to look back in history to a time when we didn't have the Industrial Revolution and carbon dioxide levels rising in the atmosphere?
Of course, that's very interesting. So if we look back in over very long periods, so for sort of hundreds of thousands of years, you can see there's a cycle, ice ages and interglacials, that are almost certainly related to the amount of radiation received from the sun. Now, however, that's not due to solar activity, that's just due to changes in the Earth's orbit around the sun. So we can see changes in climate due to changes in solar radiation. If we go to more recent history, and then you look at the number of sunspots on the sun, and you can see changes over sort of hundreds of years, as Lucy's described, there are small changes in the global average temperature that perhaps are responding to those changes in the solar energy coming out.
I suppose you must have a problem that the telescope was invented, only 400 years ago, so the best observations of the sun are only relatively recent. How do you know what the sun was doing more than 400 years ago?
Indeed, so you have to rely on what are referred to as proxy measures, so measures of things that sort of you can interpret as being related to solar activity. And the most useful one is in cosmogenic isotopes. So if we look in tree rings or ice cores, you can see that there's changes in the amounts of ratios of beryllium atoms or carbon atoms. And the ratios of those isotopes is depending on the amount of cosmic rays that are coming in from outer space. Now, the amount of cosmic rays are modulated by solar activity. So when the sun's more active, there's less cosmic rays and there's less of these cosmogenic isotopes. And those records go back a very, very long time, hundreds of thousands of years.
Now, something that surprised me reading up on this was that people seem to be talking not just about the sun's light affecting global climate, but also on regional weather systems. I would have thought the Earth was so far from the sun, but it wouldn't affect one region differently from another.
Exactly, and that's very, very interesting. So I think what we think is happening is that we've talked about the spectrum of radiation coming out of the sun, and some of that radiation is in the ultraviolet. And the ultraviolet radiation varies by more than the 1/10 of 1% I've already mentioned over the solar cycle. And that radiation gets absorbed in the stratosphere where the ozone is. And we can see signals of the solar cycle in stratosphere and temperatures and ozone. And recent studies are suggesting that when is going on, that somehow couples with the lower atmosphere, and you can get changes in circulation, which then impact, for example, the temperatures in the North Atlantic. So you can get much larger changes in Western Europe in response to the solar cycle than you do if you just look at the global average temperature.
Joanna, thank you very much.
You're listening to The Naked Scientist with Chris Smith and with Dominic Ford, and this week we're talking all about the science of the sun. Our guests are from University College London, Lucy Green, and from Imperial College, Joanna Haigh. Let's take a look at some of the questions that have been coming in. Bill Black is wondering, Lucy, how you can actually shield the power grid. So it's all very well to diagnose that there might be a storm coming. Is there anything we can do to stop its effects?
Well, we can't stop its impact with the Earth. That's absolutely certain. So when it arrives, what happens is it encounters the Earth's magnetic field. So these coronal mass ejections are magnetic bubbles themselves, in a sense, and then they interact with the Earth's magnetic field. And if you change the Earth's magnetic field, you can start to create electric currents. But the National Grid, they are interested in the very large events. There's day-to-day space weather. As I said, we're sitting in a dynamic and variable atmosphere of the sun. But National Grid in this country are really interested in the big one that could cause a lot of currents, set up a lot of currents that would then affect their electricity networks. But so they do take into account what the sun does, and they are watching it all the time. And what they can do is things like making sure that there are people at the relevant substations that need to be monitored. But they do have ways of bringing up power lines if necessary and monitoring the systems. But all this takes time, and this is why we need the forecast, the warning of what's going to arrive at us and whether it's going to have a strong impact.
Thank you very much, Lucy. Joanna Bavesh says, what effects will we actually see? What will be manifest for us on Earth when one of these things impacts? He's thinking in terms of heat, UV, or maybe phenomena in the sky apart from just weather. What do you think about that one?
Well, if you're talking about solar storms and space weather, that has very little effect on the climate and the weather down below. It's much more on the impact on the power on the communication satellites and that sort of thing.
Because Sue Hicks and de Villiers Molefi are both debating whether or not there may be some impact on weather acutely because of storms on the sun. Can that happen?
I'm not aware that it can happen, no.
Thank you very much. Well, thank you to both of you. We have to leave it there because it's time, on the subject of looking skywards, to turn to our question of the week with Hannah Critchlow.
This week we keep a steady gaze at the skies with this.
Hi, my name is Ray Gorman and I live in Astoria, New York. Greetings, naked folks. Does the expansion of space slow the speed of light? So if you're looking at the universe from the outside of the universe, would the distance of a mile a few billion years ago be less than what a mile is today? This would make the speed of light slower back then compared to now, wouldn't it? Cheers!
So does the speed of light change? Dr. Andrew Pontzen from University College London provides the answer.
So far as anyone can tell, the speed of light in our universe is absolutely fixed. It does not change.
And the speed of light travelling in the near vacuum of space clocks in at just shy of 300 million metres per second, or 186,000 miles per second. So if space is expanding, doesn't that mean that objects in space are also expanding, including atoms in our meter ruler that we use to measure distance by? Well, space expansion isn't actually uniform. Our Milky Way and the galaxy next to us, Andromeda, are moving closer to each other. But in general, galaxies are getting further apart as space expands. In this case, does this non-uniform expansion affect the meter rule somehow, and therefore affect speed of light? Well, back to cosmologist Andrew Pontzen.
As you can imagine, the fact that the universe is expanding and distances change over time does make this a bit more complicated than you might think. It even makes what we call speed of light ambiguous, because distances mean something different at different times. But actually it doesn't. You can still define what we mean by the speed of light pretty well, because it has an effect, for instance, on the structure of atoms themselves. This is through something called the fine structure constant, which is just a number that the speed of light appears in. So if the speed of light were different, the structure of atoms would also be different. And because of that, by looking through telescopes, we can actually tell that the structure of atoms hasn't changed over time, and that's what makes us pretty confident that the speed of light must be fixed.
Okie doke, rest assured our speed of light is not decreasing, and time is not speeding up either. Or is it?
There is a possible complication, which is that something called string theory, which is a possible theory of everything, sort of a better version of physics, does allow for this fine structure constant to change. So it is possible that in our universe the fine structure constant, and so the speed of light, is effectively changing over very long timescales. But whenever anybody's looked for any evidence of that, they have found no evidence. So as far as we can tell, the speed of light is fixed.
Thanks Andrew Pontzen and Ray Gorman for getting in touch with the question. Well, with the answer to that expanded upon, we sniff out the answer to this.
Hi, I'm Jonathan Michael from the Philippines. I would like to ask, what causes deodorant stains on clothes? I mean, me and my friend are using the same kind of deodorant, but he never have those ugly yellow stains, whereas I have those, especially my white clothes. I would like to ask if it is something that my body only produces while he doesn't, or it is because I'm sweating like a pig.
So are Jonathan's pig tendencies to blame for his deodorant stains? What do you think?
So if you can help Hannah, then please email chris@thenakedscientists.com. You can also tweet @nakedscientists, or you can join us online on our forum where people are debating Question of the Week. You go to nakedscientists.com/forum. Now, our quiz this week, we asked you Can you tell us the age of light that's coming from the sun? Now, the answer to this is actually a little bit of a trick, because photons of light are produced inside the sun, and some might escape very rapidly, but others will collide with particles inside the sun, because especially towards the core of the sun, it's very high in density, less so as you get further from the core. And so this means that the photons are likely to bump into other particles many times before they're able to make it successfully to the surface of the sun, and then exit and take the roughly 8 minutes to reach us here on Earth. So, doing some crafty back-of-the-envelope calculations, it could take a photon anything from thousands to millions of years to escape from the sun. So the average is somewhere between 10,000 and maybe 100,000 years between a photon being produced and the energy it contains finally arriving after an 8-minute journey across space here on Earth. That is it for this week. Time to say thank you very much to Mike Knight, Rob McLaren, David Willits, Mark Gibbs, Lucy Green and Joanna Haigh, who are our guests. Thank you to Dominic Ford for joining me, and the production was by Kate Lamble. Next time, it's one of our live shows at the Cambridge Science Centre, where we will be finding out all about what it takes to live a healthy life. You can find out how to grab tickets from our website, nakedscientist.com. The Naked Scientist comes to you from Cambridge University. It's supported by the EPSRC, the STFC and the Wellcome Trust. My name's Chris Smith, and thank you very much for listening. Goodbye.